Well, let's continue with our mini course about Poincaré conjecture and Ricci flow. And now today we'll begin the main part of the mini course. It's a great pleasure for me to introduce Professor Tian from Princeton and Peking universities. Professor Tian got his PhD almost 20 years ago in Harvard. Since then, he has built a fantastic career with working on Riemannian, symplectic, algebraic geometry, existence of Kähler-Einstein metrics on complex manifolds. And lately, he has been working a lot on Ricci flow. In particular, he's one of the authors of the book we have been following in the last 2 weeks. So, Professor Tian.
Thanks. So it's a great pleasure to be here, and it's nice to see a few friends, old friends again, and thank Marcelo for invitation. So it's a great place. So, and also I'd like to thank Louis for previous lectures. I'm pretty sure, and he did a great job. So what I'm going to do in these 9 lectures, and I want to give you an introduction to our book, the joint book with John Morgan on the Poincaré conjecture. Of course, it's not possible to go through a whole book, and it took me 1 year to do that in Princeton, so and a much smaller size. So I rather just give you, in a sense, give you an introduction to a book. I want to tell you some key arguments and key results in the Paramount's proof of Poincaré conjecture. So maybe today, it's since this is my first lecture, I just follow the standard way. I will start with a brief introduction for whole things, and it's maybe a duplicate of some of these things already done by Louis. So, by the way, so it will be presented by different persons. So anyway, so I will start with a bit introduction. So I consider in this actual concept a manifold which is compact, though it's many arguments can be still without boundary. So G denotes a metric. So locally in coordinates is just given by a positive definite matrix, and so matrix valued functions. So usually it's and we have a very classical result in and maybe I make a definition first. So in geometry now, it's we study a lot of these differential equations, which give you a character give you nice properties of metrics. So one of that is called the Einstein condition. So I say a metric is Einstein if the Ricci curvature of G is a multiple of is that big enough? It's okay.
You could write larger.
Okay. I can't guarantee that for the next 10 minutes, but then you need to remind me again. So G. Okay. So lambda here is just a constant, and here is this is Ricci curvature, and I assume you know what the curvature is. And it basically measures deviation of volume form from a constant, from Euclidean volume form. So lambda is a constant. So usually it's, you can normalize this such that lambda is given to be one of these values. Okay, it's okay. It's okay. Yeah. So why we call this Einstein matrix? Probably it's just because this is a static solution of Einstein equation in the general relativity. In that case, actually, you are considering hyperbolic equations. So here we just look at the static solutions. So why did we study this kind of particular matrix? That's because there's a classical result called uniformization. The uniformization result says maybe I just since this is for Poincaré conjecture, maybe I just state for dimension no case. If a dimension say is less equal to 3, say for example in these lectures we just assume this is a 3, so then and if M has admits a Einstein admits an Einstein metric, then the M has the universal covering of this. So this denotes a universal covering is one of these following things. So either it's a sphere, or it's a Euclidean space, or it's a hyperbolic space. Hyperbolic space. Okay. So this is the case for when the dimension is equal to 3. But you may ask why we only worry about these cases, because this theorem itself here is not true if a dimension is too big. And in that case, you need stronger curvature conditions, which I probably will discuss later in the if I have time. Anyway, so we have this classical uniformization theorem. So this actually gives a chance of proving this study Poincaré conjecture, or even more generally geometrization conjecture using differential geometric methods. So the question you can ask is, does the M have an Einstein metric? So the answer in general is no. Of course, this is true if a dimension is this is a false. Okay. So of course, in general, in the case if n equal 2, this is true because that's just the classical Riemann matrix theorem tells you. Okay, a classical theorem in a complex analysis tells you every Riemann surface has its universal covering is a standard, and actually using that you can prove that there's always an Einstein metric. Of course, that case is just the metric of constant Gauss curvature, and we know the existence. But in general, it's false. And in fact, even in the 3 dimensions, the Thorsten and showed before, there are actually 8 kinds of geometries in 3 dimensions, which you can have. So Thorsten's geometrization conjecture is basically the following. I'm not going to state precisely. So the conjecture basically says that if you are giving a 3 manifold, okay, and you can be decomposed into a canonical, in a natural way, into a pieces, okay, such that each of them is either Einstein metric is Einstein, namely that means there's Einstein metric or is a graph manifold. If you want to be more precise, what it says is you can basically cut the given manifold into pieces by incompressible tori, and such that each piece either has a canonical metric or is a graph manifold. And the graph manifold is kind of a manifold which was well understood 40 or 50 years ago. Okay, so one of the consequences of this is that implies I was warned not to cross that line, so it implies a Poincaré conjecture. Poincaré conjecture. So the Poincaré conjecture says if we have a simply connected three manifold, it has to be a standard sphere. Okay. So what the Perelman did is to use the Hamilton's Ricci flow to solve these conjectures. So let me say a few words what he said. So in the early 80s, the Hamilton introduced the Ricci flow. Okay, so this is just components of Ricci curvature here, and it's So Ricci flow is a nonlinear equation, and it has a certain has a parabolic equation modular Diffie-Morrison groups. So in fact it's not so hard to prove that there's always a local existence. So namely at 0 is some given metric, giving any smooth metric you can so this is on the. You can always solve this equation up to some time. Okay, so capital T is some positive time. So you can always solve this by up to some time. So that was already done in the previous lectures. So one of these things was known is before the Perelman coming is if you want to make a big assumption here, if say this. If we normalize the flow, so we say if we normalize flow, say this flow star has a global solution, okay. So maybe after suitable normalization, So and also assume say this global solution is GT, okay, and so the global solution means T exists for all the time. This GT exists for all the time up to infinity, and also assume this GT has a limit, as a smooth limit. So then you can prove. Then the GT is Einstein. G infinity is Einstein. So then you can use the uniformization theorem. You know what the topology of underlying manifold is. Okay. So of course here is two big assumptions. I mean I can go a little bit further, say what is a normalization means. Maybe I put it over here. So that anyway, this is so normalization. You can say here is for example, you can normalize the volume along this flow may not be a constant, but you can fix the volume. Say you can make a G tilde parameterized by different time, a different parameter. So this is some constant phi s, and also it's G of T s. So you change the parameter, and at the same time you rescale the metric, so that if you choose this appropriately, you can say this G tilde of ds it still satisfies the flow and up to a constant term. So it's constant depends on how you choose these functions, and some constant, maybe I put this way, of G tilde. And this is Ricci curvature G tilde. Okay. So R is some constant, so this way you can make this, for example, the volume of this stays as constant. So this is one way of normalizing this flow. Then you can say, okay, you can make it more precisely, say after this normalization, it has a global solution for all S. Of course, at this point, I was a little bit sloppy, say T and didn't distinguish T and S. Yes?
I'm going to return to right lateral.
Oh, okay. Thank you. Every 10 minutes. You didn't forget that. Okay. So anyway, so after normalization, if I assume there is a global solution and the global solution has a limit, then everything is okay. Everything is okay. Of course, these are two big assumptions here. And it's you already know, because I have a question. I already say this question in general is false. So namely, it's not possible to have these two assumptions in general. That's already give you. I already tell you it's not possible. So the thing is you want to say what do you need it in order to make up that things you cannot do. So of course, sometimes you can make I give an example. That's actually one of the earlier work of Richard Hamilton. You can make some geometrical assumption at the beginning. For example, if you assume if a reach of initial metric is positive, then I'm still on the three manifold. Okay, and in general, this is not true. Okay. We hope that is true, but it's not true. So if you make this assumption and you are still working on the three manifold, and he proved, and later on we will see that anyway. So this positivity of Ricci curvature will be preserved along the flow. So. And moreover, after renormalization, and then G infinity equal to limit does exist. Okay. Of course, here again, after I did this, I changed this S back to T. Okay. So namely, these two assumptions indeed hold if you make these geometric assumptions. So this will actually prove that any three manifold of M3 of this type is always the S3 quotient by a finite group. The S gamma is a finite group in SO3. Okay. It's SO4. Sorry. So this way you can actually in a sense to prove this conjecture here and these geometrical conditions. But in general, the Ricci flow does develop singularities, and it does develop singularity at a finite time. It's partly because so in general, this flow does develop singularity at a finite time. Some T0. Okay? Because it's a nonlinear equation. And then the singularity might be caused by topological assumptions, by topological reasons. For example, if the manifold does not have Einstein metric, you got to have singularities, right? If one of these assumptions has to fail. And sometimes the singularity because of complexity of geometry. So that case is the things are more complicated. So in order carry out this further of this program Hamilton started, you have to deal with these issues here. So that's what I'm going to emphasize. Of course, I cannot give you all the details, but I will tell you some of these key things and be used in dealing with the singularities. So because of this, we have to first, since Ricci flow develops singularities, so you cannot stay in a standard framework of a solution for these parabolic type equations. You have to consider. So one has to consider the Ricci flow with surgeries. In a sense, with surgery. So this of course here it's a length. So I have to give some meaning of length. So in some sense, from a PDE point of view, I want to consider generalized solutions. And on the other hand, I don't want to consider too weak solutions because that does not capture geometric property of underlying manifolds. So we need to have a solution and fairly general, but it's still does not lose the topological informations. So here is basically a definition of a solution. Okay, I just described it briefly, and in the lecture I will, at one lecture I will describe how to do a surgery process without the full details. So basically I look at the solution of MT. So I should say the Ricci flow with surgery. Even this was the first already studied by Hamilton in a four manifold case with certain isotropic positive curvatures. So here, so you consider GT. Okay, so so T is from 0 to infinity. Okay, so it's called Ricci flow with surgery. If there is say T of I guess T1 positive, because local extension has so T2 all the time. Okay, such that this first this MT in the interval, say let's make a T0 to be 0 to start with. Okay. So just for convenience. So this is the same, stays the same. It's MTI for T contain the TI plus 1. And the flow is a GT, just standard solution of Ricci flow. So when I say standard solution, just the standard solution in a Euro sense, and then so then I want to say this MT say TI plus 1 say plus epsilon, okay, and is somehow related is related through a topological change. MTI plus 1 minus epsilon. So epsilon is very small. Okay, so through a certain topological change. Operations. Okay. So there's one catch here in this definition. I make a remark here. So in this definition, I allow this MT to be empty. Of course, M0 is not empty. That's a manifold to start with. But as T grows, I allow this Okay, so it's perfect in the definition. In that case, of course, it's empty set. Anything you can put on that. Okay. So the key, of course, this definition is easier because it's way of it's easy to do that, and in some sense, it's also easier if you just construct a solution of this type, since you this type. But there is a subtlety here, namely, so basically this I draw a picture. So this M. So what you do here, basically, I mean, one thing you can do, you can start with M, say MTI plus 1, somehow minus epsilon. So then you go through as T grows. Okay, and you start to develop a singularities. Let's say, suppose you let's just draw the picture in the Riemann surface case as an illustration. So then what you can do is, okay, I develop two cusps here, or develop. So in general, you develop something like it's with a little Riemann surface as cross sections. Okay, so you imagine this is three manifold and the cross section are surfaces. So natural way to do that is you develop a certain type of singularities, and singularities is kind of thing modeled over Riemann surfaces. So then what you do, you can somehow cut off the things. You can cut off this along here and remove the part where it's too close to cusp, and try to fill in different things. You get maybe you get something. Something on the different manifold, then you start to flow again. So now this is Ti plus 1 plus epsilon. Okay, so this is part you do surgery, basically cut off this part which is too close to cusp because the curvature becomes very, very big, and then you fill in things and become a smooth manifold again. Then you evolve the Ricci flow again. So the key point here is of course this is nothing against the definition here. The key point in the things is in order to be topologically useful, one needs to only this cutting surface. So the point can only be a sphere. Because it has been known for a long time, if you, for example, even you cut along the tori, and you can produce any manifold you want. So if you cannot prove your surgery part, it's only you can only need to do a surgery along the spheres, then it's not useful, because analytically you can still do this establish a long time existence of Ricci flow with surgery, but topological consequences will disappear. Okay, at least not so clear. Okay, so one of the key points is you have to make sure this. You have to make sure this. So that is basically a breakthrough of Paramount. It says this is the Paramount's first basic things. I made sure this. So you only need to do a surgery along the S2s. Okay, so then the topologically is much more much easier. So let me state the general theorem, which is basically main theorem in our book. Even though my book only aimed at Poincaré conjecture, but this theorem is also a core part of geometrization conjecture. So let me state this. So let M is a three manifold T0 be be a closed. Any questions? 3 manifold. Okay. And then there is a Ricci flow. So there's a Ricci flow with surgery. Okay, so let's see which surgery say MT and GT, such that, of course, G0 is just the initial metric. Okay, and more things. So maybe let's suppose this is 1, and the 2 is this Ti. There's no accumulation point for any finite time. So for any t, there are only the set of Ti contain the 0t is finite. It's finite. So you only need to do surgery time at any finite time. Okay. So within a finite period of time. So last things is so you might have a countable, you might have an infinite number of surgery time as indicated here. So Ti stands for surgery time. I just by following a notation here. So last thing is important. So each time you do a surgery is a following. Now topological change. So one crossing Ti. Okay. So when you're crossing a surgery time, so a 3 manifold topological change in MT. So it's given by is simply a connect sum is a connect sum of the following things of a connect component. Components of following type. Okay. So first is S2 cross S1. Okay. And RP3, connect sum RP3. Or is S3 quotient by a finite group. Gamma is contained SO4. Okay. It's a finite. So of course this is the key thing to be established, and I in my lectures, following lectures, I hope I give you a pretty complete ideas how this can be carried out. Okay. So to finish up the introduction, so maybe I want to say so when we come to Poincaré conjecture, is yes. Hmm?
Should be positive curvature.
You mean this one, positive curvature?
No, because when it appears some part of graph manifold, it
This is a surgery time. I didn't say about long time extent.
Your initial Riemannian manifold is there's no assumption about the curvature of G0.
No, I don't need the assumption. So here I only established is a solution t from 0 to infinity. I didn't tell you when the t goes to infinity, what happens yet. Then the graph manifold comes out. Okay. So again, I said this when I say solution here, empty might be empty. So that's what I'm going to say now. Okay. So in order to prove Poincaré, for proving a Poincaré conjecture, so what you want to do is what the Perman try to prove is to prove there are two ways. First, of course, you can prove general. You give a proof of a general geometrization conjecture, or you want to have a shortcut to prove this the empty become empty. Okay. So if a t become empty, then of course since each time you know how surgery was done, and you capture all the topological types. Okay. So this is the way of proving a Poincaré without proving a full geometrization conjecture. So the way to do that, how can you make sure this Ricci flow will become extinct? So like this here, after certain time. So in the case of this example I cited, the Hamilton used the positivity of Ricci curvature. For example, this can be easily established if you assume a scalar curvature is positive. Okay, so then this is easy. This is easily true. Easily proved. So maybe I put this way. If a scalar curvature is positive of G0. And that's also known long time ago. So that's already included the case like Hamilton did. But in general, without any geometric assumptions on the initial metric, what was done was actually also very interesting. Is Perman introduced these things. So assume this is now let's say assume this MT is M0 is simply connected. For simplicity, actually you just need the assumption fundamental group is a cyclic or something like that. Okay, so let's make this. Then what you can do is you can pick up this. You look at the loop space of M0. Okay. Contractible loops. Okay. So then the pi 2 of this is not 0. So you pick up some class here. So you can define the following things. Okay. So define the following things. You define you take all loop here. Take loop here. So this is giving take infimum of all of these. Maybe I put this class here, and take all fix the beta class. Okay, take all of the cycles. Take all of this map from S2 into here. So then you take a supreme of for beta now. For each of these beta here is S2 into your loop space. Into your loop space, yes. So now what you can do is you take any of these. You take area of this, which I will define, of beta of sigma. Sigma is S2. So this summation, this supreme is taken with over sigma here. over sigma here. Okay. So basically you have S2 family of loops, and you take I haven't defined this, but you take a maximum of this, whatever this. So this is so this depends on metric, because this will depend on metric. Okay. It depends on the class you choose. So now let me define this. So what is this? So A of beta sigma is simply the infimum of all the disks, such that the boundary of disk is given by this loop, and you take area of this disk. Okay. Okay. There's a dual version of this was alternatively given by Coding and Minikowski. Actually, in that case, use S2, S1 family of S2 surfaces, and in that case, you define correspondingly. But this one has a little bit advantage in the sense is when you use areas, you still use the minimizing area. Okay, so 2-dimensional thing is minimizing, but then you maximize among all the possible family of loops. So what Paramount did is using these things to prove these things actually. So actually, his proof was very sketch. So you probably detailed proof was given in our book, which is much longer than the original proof. So now these things is this W, the derivative of this. You take a derivative along the Ricci flow. Actually, it's not for simplicity. I just state for standard solution Ricci flow, but you can state for Ricci flow with surgery, because when you cross surgery, this actually decreases. So this is less equal to pi. I just make it for t. So this t0 may depend on your initial metric. Okay, may depend on initial metric. So this way, as long as the Ricci flow with surgery exists, you can compute the directional derivative, and you can prove using a Gauss-Ballet and variation of areas to prove this derivative is strictly negative. So that will imply T is big enough, right? So I better write up. So that's imply a Poincaré conjecture. Okay. So in general, for geometrization conjecture, what maybe I just, so what you need to do two more things. So one thing, you already have this solution, so you study asymptotic behavior of GT. So you have this solution with surgery. So that means as t goes to infinity, So basically, so this was done in two sections in the second paper of Paramount, which was second paper was considered the technical part of the whole proof, and but that's not quite a surprise here. Basic arguments, except that there is one part one uses Alexandrov spaces to bound the curvature, and so then the arguments are more or less adapt the long arguments. was discussed, used before by Hamilton and others. Okay, so then what you need is a collapsing result. On a 3 manifold, M3, with curvature bounded from below. Actually, with curvature bounded from below locally. Maybe I should put locally bounded from below by some constant. Okay. So the more precise what he did is because by studying asymptotic behavior, you can decompose the manifolds into 2 parts. One part is a so-called thick part, where the curvature is bounded, actually. Okay, so then that part using standing long arguments to prove that part actually converges to hyperbolic pieces. Okay. So then there's another part which is a thin part. That part is at every point, near every point, the curvature is somehow bounded from below, compared to the size of volume of a unit ball with center at that point. So that's called the collapsing part. And you want to prove that collapsing part is a graph manifold. It's a graph manifold. And so Perman actually stated the result without actually giving a proof, but he indicated what where you might able to find arguments, similar arguments for this, and this relate to this. This is very much related to these 2 Japanese work, Shioya Yamaguchi things. Okay. So anyway, we are John and I are actually writing up a proof of this, and it should appear soon. So this is roughly what outline what Perman did, except in the last minute I was quite less. I mean, whole thing is outline, but last one is even faster. So, any questions? I move on. Yes.
Because I got lost in this definition of area.
Yes. Okay.
Could you explain it a little?
So for each sigma here,
Yes.
so look at all the map from S2 into a loop space. Okay.
Yes.
So for each of these parameter which is in the S2, you get a loop. But loop is contractible, so it bounds the disk. I assume simply connected at the moment.
But the image is a set of loops. It's not a loop.
No. Beta, for each sigma, the image is a set of loop, that's right. But for each sigma, it's one loop.
But it may be a knot.
Huh?
Maybe a knot.
What is a knot? Say it again.
Yes. Figure 8 knot. It doesn't want this.
Why is a knot? I mean, it's still a bounded disk. I mean, it's not bounded embedded in the disk, so I don't care. Huh?
Knot.
Okay, so you want to be more. So what I say here is an image of a disk. Is that it make it better? Okay. Into your manifold such that the boundary of FD is boundary of F is this. Okay? Or maybe more precisely. Yeah, because it's okay. We got in this last chapter of book, which is to prove this, and we got some referee report. I'm sure it was topologist, and he was very. We need to spend a lot of time explain why it's not embedded. So here we don't need to embed the disk. That's the point. If you either embed it, of course, it's complicated here.
It looks a little bit like extreme length for building an all this sort of reminds a bit of extreme length. You have the sort of on-topic laws and curves, and then you look at the. But it looks a little bit like extreme length.
Yeah.
Extreme length. You have the sort of on-topic laws and curves, and then you look at the. But it looks a little bit like extreme length. You have the sort of on-topic laws and curves, and then you look at the. Well, it's not quite the same, but it's.
I think there is actually when I was giving this course in Princeton, I was actually quite curious about that, but didn't get time. So there are some maybe. I certainly like to know more reference on these things. I'm sure this kind of thing was discussed before. And for example, in the analysis, there are certain things they call there's certain analytical problem studied like that. But it was nicely used here.
No, it has a little bit of the same flavor as this extreme length, this wording and almost.
Okay.
It's not quite the same flavor.
Yeah, and certainly we'd like to talk more on that later. Okay. I think I have to be fast now. So let me say a few topics I will cover in this course. So maybe I write down quickly, and because so basically what I want to do is in these 9 lectures, actually today, and so first I in the following what I want to topics. So first is easy one, because I try to finish it today, is the evolution of curvatures. And the second, which I do next time, is maximum principle and its application. So basically here I want to do is a key estimate is called a curvature pinching estimate. That's why 3-manifold case is used, 3 dimensions used. So each time I promise to prove one theorem, I cannot prove each time, almost each time. So I want to prove this curvature pinching. So third topic I want to do is the paramount reduced. Length and monotonicity. So that's the key technique introduced to make sure this. Fortunately, I didn't erase this yet to make sure this. So then is the proof of non-collapse results. So let's put that more into context. So non-collapse result by using this reduced length and then exclusion of. So the consequence of this is exclusion of a cigar solution. Okay, just as an illustration to see, you cannot do a surgery along the tori. Okay, So then this part I'm not sure I can give all the details, but I will describe it because it's rather technical. But it is another, in my opinion, is another crucial part in the proof. Is I need to bound the curvature. So it's bounding a curvature. I give a name. It's bounding a curvature at a finite distance. At a finite distance. Has bounded distance. So the reason to that is we know once rich flow develops singularities, is a curvature blows up. Okay, so this part tells you how to analyze how to analyze this, how to analyze the part where the curvature is big. And so then I want to I think this 6 may be dropped because I want to discuss a little bit of standard solutions, but I may just state property now. Okay. So then I describe surgery process. And so I may need to, I think I most likely I will squeeze a lot of time here in order to describe, spend more time on describing a surgery. And the properties of Ricci flow with surgery. Okay, so then I will go to this finite extinction to tell you. So that means to put more details on this part. Okay. So if time permits, I was thinking about having one lecture, but I'm not sure. So it's I want to describe a little bit of geometrization conjecture and to outline things on here. And it's also possible, and I will discuss some of these things, geometric aspects of four manifolds, which I think might be interesting to study in the future. And of course, I have to give a talk at the colloquium, and so I will probably take that opportunity to fill in whatever I didn't write here. Okay, so let's do a serious stuff. So let's if you have quick questions and. Okay, so let me talk about the evolution of a curvature, and it's not that difficulty. It's a lot of time. It's like just tensor calculations, but it's nice tensor calculations, and it's tensor calculation with time. So let's consider the Ricci flow. Okay, so it's this is on a, say we already know this, it exists at finite time. So let's say it exists here, and it's the initial given by initial metric. So then what you can do is so let's recall some standard formulas. So G depends on T. So we know the crystal symbol is given by so this simply the coordinates, okay? In any coordinate here, G, J, K. So then you look at the corresponding change of this crystal symbol with the time. You can easily see this. Of course, this is not tensor, but after you're taking a derivative, it's a tensor. And then you can see you simply try to. You can even make an assumption. This at the point you are computing, the derivative, first derivative vanishes. That's a standard way. So then what you can do in the end is you just get this half of GIL. So then what you get here, just you take in place of here replaced by covariant derivative of dGL air I dt, and so on. Similarly, so here is j of d, sorry, this is k. This is k, I'm sorry. This is j. This j, this is gg air k dt, and so on. Okay, you can easy to. So now you bring this in. So here I change to a coherent derivative, so I don't need to worry about the taking derivative of this. So now you plug in your equation. So sorry, this is this, and you get this is minus of gi air, and so then this is Ricci curvature, air j, and then the coherent derivative k, I air k, j. I record this because later I use this a little bit, and then last one is jk and air. Okay, so that's a change of a crystal symbol. So now you use the equation. You do the same thing for curvature. What you get is the following. So you know the curvature is given by ijk air, and this is given by djk air dxi. And plus a quadratic term, which I don't really care. Quadratic term on the gamma. Okay, quadratic term. So then you compute the derivative of this. You will get again u t. So you will get this things coherent derivative I. So you don't need to worry about that because once you change the coherent derivative, you don't need to worry about that. T and minus j of d I k air dt. So now you plug in these things. So now you replace this by that, and you play around. Okay, you play around, so eventually we'll get the following thing, which I simply stated now. So I state the theorem proposition, which is the following. Then so you look at the curvature ijk air dt, and here is ijk air is I p of g air p. Okay. So then you can write this as a Laplacian of ijk air. Okay. And plus this twice of b of ijk air and minus ij air k. It's actually even complicated, but there's a certain rule here, a certain symmetry here you can play, and plus I k j air. Okay. And then you have something which is of g p q of p I q k, sorry, j k air. Ricci curvature IQ, sorry. So then you just change a p to each of these. So next one is just I, p, k air, and j, q, and so on. You have two more terms. Okay. So just next one is just replace k by p and replace j by k here. Okay. So this is from a direct computation, but you might worry, how did I get a Laplacian here? And why here you simply get, because of this, you will get a second derivative second derivative of a Ricci curvature. Now here you use so I just give a hint here. So hint here is the Laplacian of this. Okay. So if you write in terms of suppose in terms of orthonormal frame, so this is PP. Okay. Suppose I choose the point. I choose the coordinate such that at the given point is forms orthonormal basis. Then you can use the second Bianchi identity. So you can take this to be a I, J, L, P, K, P, and I, J, P, K, L, P. Okay. So next you switch these two derivatives, you will get some quadratic term. Sorry, I didn't give you a B there. Here, where the B, I, J, K, L is a quadratic term. So it's G, GPR, GQS, IP, KQ, JQ, KRLS. So it's quadratic term. How do you get a quadratic term? For example, if you switch a derivative here, you will get some quadratic term. So for example, you switch a derivative here, so you get some quadratic term. Okay, I leave you to work out the details. Okay, anyway, it's a standard in the. So then you use the second Bianchi identity again. This time you will say IJP. So what you get is I. Okay, and it's I and J P L P and I K and so on. You use the Bianchi identity again. So you get four terms. So each time now this your summation over P, so this become a Ricci curvature. Okay, you will get four terms involve a Ricci curvature and second derivative Ricci curvature. And then you go back to check. This actually coincides with what you get here. Okay. So then you because here you will get for first note you get 6 terms, but 2 terms cancelled. You will find here you get 4 terms left for quadratic for second derivative of Ricci curvature, and this matches here. And of course, then you need to work out the details to see a quadratic part is exactly given by this. Okay. Quadratic part. The quadratic part comes out from a change of derivatives. Okay. Change order of the second order derivatives. So in the end, if you're familiar, maybe spend less than 1 hour to work out this. Some people may spend 2 hours, so it doesn't matter. Okay. I will spend 2 hours. So once we have this, what I want to do, that's the main topic I want to do it today. I want to put this into a better form. That's due to Hamilton. I want to put this in a better form because I don't want to see too many of these indices there. I want to put this in a more cleaner form. Okay. So what we do is we instead of looking at this equation in the local coordinates, what you can do is you can write this evolution equation in the moving frames. So you try to use a frame which may depend on a time. So more precisely what you do is the following. So what you do is you consider the frame, define orthonormal frame, define a new frame, Fn. So what I'm doing today actually from now on is can work for any dimensions. So of course this only defined locally. So this is the frame is given by this. So this depends on time. Okay. So this is you look at the Ricci. Those are vector fields. So this for tangent space on some open set. Okay. So then you look at FA. So this becomes one form. Then you look at the dual of this one form. Okay. So more precisely, if we write say FA to be in terms of coordinates, A of I in terms of local coordinates. So then this equation simply says those are function of t and x. Okay, so this is ODE we're doing here. So for G of I air Ricci curvature of air K and F K of A. So then there are a couple of things you can easily check. Maybe I state a lemma here. So lemma tells you this is orthonormal. So if suppose that this FA0 is orthonormal basis. Normal basis for G0, then so is so does. Okay. The reason is the proof is very simple. You look at the GT. Then you look at F, look at G, look at this function, FA, FB. It's a function of t. You compute this. And GT evolves along the Ricci flow, and this evolves this way. You can easily check this is identical to 0. Use Ricci flow and this equation here. So the pairing stays as a constant. And stays as constant. Okay. So moreover, what you can do, you can make a following observation. So if if you have another basis initially, say this prime, the theta of IA of 0 initially is another frame which is given by some AIJ, say at initially of j of A of 0. Okay. Maybe I put this way. I'm sorry. So this is I of B, AB. Okay. So and this is also normal basis where since are both also normal basis. So this matrix A of A, B, A is in ON. Then you can easily check the F theta of IA of T is still is A of B of AB IT, and A stays a constant. So this way you find this is not does not depend on choice of local coordinates, only along the time. So that implies that there is actually the phi t from a tangent space to itself. Okay. So it's a change of so it's a bundle automorphism. So this is a bundle automorphism. Bundle morphism. And such that with phi 0, of course, is just identity, because at the okay, which you can construct by using this frame here. Okay, such that phi t star of gt, just a phi g there. But don't confuse. So this phi t, family of phi t, is just a bundle morphisms. So, but they are not defined, induced by diffeomorphisms. Okay, if they are induced by diffeomorphism, all these metrics are the same. There's nothing more to do. Okay, so this is just a bundle diffeomorphism. So curvature of this still could be different from curvature of that. Okay. So the way of doing this has an advantage. We can write, we can eliminate some of these terms. So what you do here? You write a curvature in a new frame. Okay, so you can either write your curvature as R A B C D of F A in terms of curvature is a coordinate tensor C D, and this F up this is a dual basis. So these are contained in the cotangent space. It's contained in the cotangent space. So once I do this, you can. This is equivalent to say this component. These are curvature components in this frame, and you can also compare them with a frame in the fixed local coordinate system. So that's giving like this. It's okay. So this is in a fixed coordinate system, and this is in a moving frame with time. Okay. So this depends on t. Okay. So once you have this, you can look at this equation here. If I look at this equation, okay, and this term all depends on Ricci curvature and the curvature. So if you compute the derivative of this, you compute the derivative of this A, B, C, D, T. Okay. So then it involves things. First, you have a curvature of this, time derivative of this, then the frame here, then the plus the curvature of this, and time derivative of frame, and there are 4 terms of this. You have to take the time derivative on each of these terms here. Okay. So now use the equation for frame change. You will find this exactly cancels these things here. So what you get in the end is you will get this is Laplacian of R A B C D. Okay. So and plus twice of things there. You just B A B C D and minus B A B D C. And B of AD, ABC, and plus B of AC, BD. And these are gone. Yes, gone. So A, B, C, D are just defined this way, where the B, A, B, C, D, capital B, A, B, C, D, is just given by this A, P, B, Q, and C, P, D, Q. So why I can drop the metric now? Because I'm using this. So in the local coordinates, this local coordinate may not be also normal frame. But this frame I'm doing here is an orthonormal frame. So the metric become an identity and become an identity. So these metrics here simply become a delta and canonical symbols. Okay. So that's why I can do this. So in the orthonormal frame, I don't need to distinguish a tangent or cotangent bond anymore. Okay. So of course this little convenience is not that important because we do that all the time. So what is nice is the following proposition. You can write these terms in the further way as follows. In a further way as follows. Not so bad. So now you look at choose the orthonormal basis. Basis of this. Or here I'm not distinguishing this with cotangent bundle now because I'm choosing orthonormal basis. Okay, so metric become an identity between these two things. So then the orthonormal basis is given by phi 1 of phi n minus 1 over 2. Okay. So then what I can do is I can look at the phi alpha acting on a frame. So this is a component of these bivectors in terms of this moving frame here. Okay. So here I simply write down, I think of this as a form. So this time I look at this as a form here, and this as a vector field. So this acts on that. So that's a component of that. Okay. So of course you can even make it this just a wedge product of this. Okay. And then this become even more explicit. So then the curvature, you can write the curvature as the curvature operator of T of alpha beta of beta, because using a symmetry of curvature CT. Okay. So this time T you can think. So here where the T is from you can think it's a wedge product. So this is this here. Let's just make it easy. And this is symmetric operator. So T and so cliff. So those are components of this. So I simply look at this as a curvature, so-called curvature operator, and write this as a symmetric matrix in this frame. So then we have a following easy way to okay. So then the evolution of notion of this curvature operator is so this is actually given by in a way is given by phi t of this star of pullback of curvature operator in the local of GT. Okay, so it's given by d of alpha, d of dt, and then plussing of this, and square of this. This is a matrix here, square of matrix, and plus another operator, which is more usually it's tricky to analyze. So how do I define this operator here? So where is this is defined this way? So we define this t this operation here. So square of alpha beta is just a product matrix. Okay, it's a product matrix, and the T of this is given by C alpha gamma delta. Okay, so the coefficients here is given by this. It's a metric, and then the bracket is so again, what is a bracket here? So the bracket is because this is it's basically the algebra structure SO2. So this is a structural coefficient of small SON. Okay, so it's the algebra here. So more precisely, you can define giving two by vectors. You can define this just G in terms of local coordinates. You can define just I and Ij GKL of U of Ik V JL minus of J and Ik and U JL. Just standard matrix. Okay. It's just standard regarding this as schematic matrices, and then it's the algebra. So this is just the coefficient and the algebra.
What's
yes?
T? What's T?
Pardon?
T over J on the top, right top.
Oh, sorry. So we have this. Maybe I have 3 minutes. So let's finish a proof of this, and so let's prove this proposition. It's rather simple. So maybe before this, let me make a remark here. If n equal to 3, okay, then this is easy to even more explicit. So this is simply a adjoint matrix of T. So this is just the inward determinant of J and then J inverse. Is that adjoint? I mean, so it's a cofactor. Okay, maybe I put it this way. So cofactor matrix is the right word for that. I'm sorry. So that's okay. So I think it's just that. Yeah, it should be determinant of then the inverse. Okay. Okay. So that's a 3-dimensional. It's very explicit. Okay, that's probably I will use anyway from. But anyway, in a few minutes, I indicate how the proof is. So and actually not indicate. I give you a proof. So the proof. So basically, I use the Bianchi identity. So this first Bianchi identity say A, B, C, D plus A, C, D, B plus A, D, B, C is 0. The first Bianchi identity. Okay. So then what we can do is you look at the sigma, this EF, okay, and R A B E F, R C D E F. So this you can first using apply a Bianchi to each of these terms. Okay. So apply Bianchi to each of these terms. This is minus of A E F B and minus A F B E, and then the R C E F D minus A C F D E. So then you multiply them out and collect the same terms. You will get this is twice of this B A B C D minus B A B D C. So you multiply them out, then use definition for B, capital B. So on the other hand, this hand, if you use so I guess this side, now you replace them by this. You use this formula here. You use this formula here, you will find, you plug them in, then use the phi is also normal basis. You can immediately prove this is a square of alpha beta of I, B, C, D. So you can see this is already two terms. So this is the two terms here. This gives you a square term. So what you need to do next is to check these two terms, give you this, give you that. Okay. So maybe I stop here. So anyway, it's a straightforward computation now. So so what next is you look at this twice of 2 B A C B D minus A D B C. ABDC, sorry. Okay. So this will give you, this. So what you do is rather straight too. So you just plug this in, then you collect, then you just play on this, and using this formula here, So this you can have. Okay, so here you use the formula, use this use formula, then use this formula is just the alpha beta is C alpha beta gamma. So you plug in these things here, and using this, and do some simple manipulations, you will get this. That's end of talk today.